Hi, welcome to the Signal Pack. In this episode, I have another exciting review for you guys. We'll be taking a look at the Keysight MXR. Now, I've known this instrument is coming for some time, ever since I reviewed and did a teardown of the Keysight UXR, which is the world's fastest oscilloscope. The acquisition system of that instrument was going to find its way down to an 8-channel oscilloscope, which is, of course, the MXR. And there are a lot of additional hardware functions built into the ASICs directly that includes digital down conversion and real-time spectrum analysis that is done in hardware. So I'm really excited to take a look and see how they've managed to put all that function into an 8-channel oscilloscope and what additional features and softwares are available. This is going to be a 2-part video, and in this part we're going to look at the teardown, we're going to look at some of the new features and capabilities and experiments, and we'll do a lot more system level experiments in the second video. If you look at the description, you'll find individual jumpers to different sections of the video. So let's get started. And here is the Keysight MXR-608A. This is the highest configuration of the MXR instrument possible at 6 GHz, 16 gigasample per second, 10 bits per channel. And this is totally independent of the number of channels. When we do the teardown of the acquisition board, we will see exactly how they have managed to do this and have a fully independent control of all the acquisition channels. The design is really quite nice. It's a nice evolution of the S-series oscilloscope. All the front-end BNCs, you can see, use the same probing connectors as the previous generation, allowing you to reuse all the entire ecosystem of parts you may already have. It's actually really quite small. The depth of this instrument is only 8 inches, which means it has a very small footprint. And for what is in here and how much capability there is, this is really nice and small, allows you to use it in a lot of different scenarios in the lab, of course. Now, in terms of the screen, we have a 15.6-inch Full HD multi-touch capacitive LCD display that supports multiple displays, so you can actually have multiple channels showing up on different displays. It doesn't just replicate what's on over here. And I'm very happy that it's not very reflective. As you can see, I really don't like reflective LCD screens. This is one of the better ones I've actually seen on instruments so far. In terms of control over here on the right, it's minimalist, as what you would expect from here. We have 8 channels with different controls and LEDs in the back side, which light up depending on which one you have selected, and that would be the vertical control. Horizontal all the way to the top. I appreciate them being far apart so you don't mistake them, and the marker as well as multifunctions are all in the middle. We now have an RTSA button in the front, which we will take a look at during our various experiments. I think, yeah, they've done a really good job. 2 super speed USBs in the front. Everything looks really good. Very high quality BNC connectors and fairly rigid, and we'll take a look at that as well and see how they connect it to the acquisition board. Overall, I really like the design of this. Let's take a look at the side. And here are the rest of the interfaces of this instrument from the side. We have, of course, the PC over here, and we do have the VGA connectors still maintained, which is great because a lot of the labs still have VGA displays in them. There's also a display port for more modern units, of course, as well as the host and various device interfaces for the USB, Ethernet, and sound. It also has a removable hard drive, which is also very good because in a lot of scenarios you want to get rid of and erase confidential information, and you can just completely remove the hard drive. There's no risk of any data being exposed to any other vendor, so having a removable hard drive also for upgradability and recovery of data is very good. From the top to the bottom, these BNC connectors, we have the waveform generator output. This thing has an arbitrary waveform generator built into it. There's also an auxiliary out, as well as a 10 megahertz in and out, but there's also an auxiliary trigger, which means that you don't compromise on having to use one of the 8 channels for triggering. This does have a dedicated trigger input on the side. There are some differences between the 8 channels and the trigger. We're going to take a look at that during the teardown. Overall, I would say it's quite nicely compact everything, and MSO is over here, and we have an auxiliary trigger output too in order to sync the scope with some other instrument if you need to. Power input, 650 watts maximum for all the 8 channels. That's a lot of power. There's a lot of computation going out inside this unit. Now that's the fun part. Let's take a look at the acquisition board. And let's take a look at this beautiful Keysight MXR acquisition board. And the way this is put together is somewhat different from the competition. For instance, the main big PCB does not actually house the acquisition devices itself. It has the front end as well as the trigger and some FPGA functions, but it doesn't have the data conversion memory and the ASIC that processes the data. And that means that the way this is configured has a different cost profile. So if you want only channels 1 to 4, which are these, you will get one acquisition board. And if you want a channel 5 to 8 as well, then you get another one. That means that the upgradability can have lower cost initially because you don't have to have one of these on both of these populated. It also makes it repairable in a totally different way. If the acquisition is damaged, you just simply replace the acquisition. You don't have to worry about the rest. And the acquisition needs a PCB that's quite a bit more complicated than the front-end PCB. That also reduces the cost of how this is put together. There's a lot of work that's gone into building this. We'll talk about it in details. So let's look at the front end here for a moment, and you can see the channels 1 to 4 and channels 5 to 8 look a little different, and that's because they were experimenting with how to isolate these channels from each other. The isolation here is really critical because this board is not that big, meaning that let's say that channel 8 is set to 1 millivolt per division and channel 7 is set to 1 volt per division. That's a factor of 1,000, that's 60 dB, meaning that if you have a large signal on this channel, it will impose itself on the neighboring channel and get amplified by the front end, so the isolation has to be really, really good, much more than the difference between the gain of the two paths, and we will be able to test that as well. You can see the connector over here. This connector has the analog front-end interface going into the acquisition, and you have a digital connector over here at a 90-degree angle. They have separated these, of course, so the acquisition board can have a very well-controlled front-end analog interface, and all the digital data can be dumped out into the main board for display, and so on from a different connector, and we can look at that in detail too. There is an FPGA here that is probably some glue logic, some interfacing between the acquisition board and the main board here is handled through this, and there is one of these under this one here, which we will see. So that all makes sense. So let's turn our attention to the front end and see how that is built. Now, there are very few companies that can actually build an end-to-end oscilloscope with almost everything being a custom IC across multiple technologies. This is a huge cost for development. And as I said earlier, some of the UXR development, especially the acquisition, has found its way into the MXR, which is fantastic, and that gives huge performance benefit, especially from memory and sampling and independent channels all directly onto this. We will see that too. So let's take a look and see. Let's follow, for example, this channel. We have the BNC coming in. We have an RF relay. This is a non-solid state relay, of course. That's typical for these instruments because you don't want to have a solid state front end. And that separates the 50 ohm path from the 1 mega ohm path, allows you to switch directly into the 50 ohm or into this relay, then has multiple paths for the 1 mega ohm. And that way you can have your high impedance path and the 50 ohm path without interfering with the 6 gigahertz simultaneous bandwidth that all of these channels have. The single-ended signal coming out goes through two small ICs. These are also Keysight made parts, could be amplification, could be protection, could be attenuation, and then it goes into this main chip. This is the Keysight's front-end IC, which handles all of the different gain levels and attenuation and the multiple paths going in and converts the signal to differential. So there's a lot of functionality built into this, and of course all top oscilloscope manufacturers have their own front-end IC because the entire linearity, noise, and how this front-end behaves is going to be essentially determined by this from this path over here, and Keysight has excellent noise performance, of course. Now, once the signal comes out of this front end, it's differential, and then all of them are collected into this main connector. And if you look closely, and I'll show some close-up photos, these are differential microstrip lines going into this connector. But there's also a stitch path around it to somewhat emulate a coplanar environment. It's basically a wall of ground that follows the differential line as it makes it here. They can't do coplanar very easily here because there's no room to have, a ground pour everywhere. But this is an isolation path. It's a very interesting thing. You have to simulate this very carefully electromagnetically because it's a difficult thing to visualize and to predict. So I'm sure this is all done in quite a extensive way to get this kind of performance out of them. So once you add this connector into the acquisition board, then it's all handled over here, which we can take a look at separately. Looking over here, we have an OCXO, which is very close to the 10 megahertz reference coming in. That's where the switchover happens. And at the same time, there is a 100 megahertz crystal or a VCO here as well, which means that this guy is going to get locked to this guy. And then there is a PLL on the other side of this board from TI, which is called Platinum RF. Those are the highest performance versions of these PLLs that TI has to offer. It's essentially world-class performance at about 45 femtoseconds of integrated jitter into the 10 gigahertz, 14 gigahertz range, which is excellent. So you have a multi-stage PLL and a very complex PLL structure overall in order to not only sync all the FPGAs, triggers and everything, but also to give clock to the main front-end acquisition. Remember, these are 10-bit A to D converters that we have here, and you have to have excellent clocking to even be able to get that performance out of it, let alone all the noise that you need, of course, from the front end. And we'll see that that's on the other side of the board, and ultimately that makes itself into this IC, which is another custom Keysight IC. I think I can remove this. Can I? There you go. Yeah, it is a custom IC, and it has some clocking functions built into it. I'm not exactly sure what's going on inside, but by looking at the traces coming out from here and here, going into these two connectors, that is clearly giving the clocking for the entire system. They're probably clocking this at very high frequencies, in the maybe in the orders of 10 gigahertz and above. So that takes care of all of the PLR architecture in the front end, and then we can go ahead and take a look and see how the trigger is handled. Now, the triggering of this system is a little bit different than what you would expect. And the reason is because there is a front-end trigger IC here. This is also a custom IC made by Keysight, and this gives you all of that excellent multi-level, very sensitive, and all the advanced triggering functions that you're used to seeing on the 4-channel oscilloscopes that Keysight has been offering so far. And this guy is fed from these 4 channels. Now, if you want to have all of the multi-level triggering functions on 8 channels, you will need 2 of these. So Keysight has made a somewhat of a compromise, saying that you can have all of the really good triggering from the first 4 channel, and the other 4 channels are going to give you okay triggering, not excellent, not as good as this, and that's because they're multiplexing and feeding this back into the same triggering IC, so you don't get all the functionality. If they didn't do that, they would have to have 2 of these, and it would make the board quite a bit more complicated. It's really a compromise decision, which is okay in most cases, because if you ever need some of the advanced triggering, you would have to just switch the channels and you would get that. From everything else, all the channels are essentially identical except for the front-end triggering. This chip over here, this is actually an FPGA, and I think I should be able to remove this because I think I already did. There you go. There it is. This it's a Xilinx FPGA over here, and I think this is called the Kintex. Yeah, that's right. This is the Kintex platform. These are fairly complex FPGAs, and this handles the wave generation, the frequency counter, the displaying, and so on. So this last piece, this last computation port is not done in custom IC. It's done in custom firmware that is built into the FPGA. This is, of course, custom. So looking at this from the top down, everything here is almost custom. I mean, starting from the very first chip on the front end, this guy, this over here, the trigger, the acquisition board, the front end IC, these are all Keysight parts, and almost end to end, which is quite incredible. This block over here with the 2 relays and some resistors, this is responsible for the waveform generation, because this thing can do an arbitrary waveform generator that's built into the instrument that's fed from this guy. Now, what I cannot find is where the DAC is on this. I couldn't find the DAC, but there is some analog switching for the different amplitude levels, and this trace coming over here goes down over here, so that's the analog. This is the wave generation output. That also all makes sense. The MSO over here coming in gets reconditioned by some of these front-end ICs and find its way out into the FPGA. I believe these are 2 gigasample per second SerDes that then ultimately make it into the display. So that's handled through this path as well. And let me see what is missing. I think we might have to now move on to the acquisition board because there's a lot to talk about over there as well. So this comes off. I should be able to remove it. There it is. So now you can see on the other side, look at those capacitors. Wow. And if you look at this board has quite a few more layers than this board does. And that's what I was talking about, that it is different. I mean, what I'm holding in my hand is an incredible acquisition board. This is a 4-channel at 16 gigasample per second with hypercube memory, with independent channels. It's incredible. So we'll take a look at that. In a second, you can see underneath it, we don't have really anything that different. We have power coming in over here from several different connectors, and power management is all on the other side of the board. So it's also, it's likely that some of this power management is actually not on this board. I don't have the other board that probably does some of that because I don't see a lot of DC-DC converters on this. Let's flip this on the other side. And here's the back of the board, and did I say it doesn't have a lot of DC-DC converters? I was clearly mistaken. There are a ton of them in the back here, controlling all the different voltages various analog and mixed signal components require. And yeah, it's beautiful as you would expect. And this is the back of the various ICs. Here's the back of the FPGA. You have some flash memory over here, most likely responsible for the arbitrary waveform generator and potentially storing some firmware for the power on. There's some bodge wires on this, but of course this is a prototype. This is not how this instrument is shipped. And here are all the BNC connectors. And one of the things about these BNC connectors is Keysight is, I would say, somewhat unique in putting extremely high quality front-end connectors that have very, very good high frequency response. And they did this in the S-Series scope when it initially came out, and I'm very happy to see them over here. Excellent mechanical stability in the front end connecting to the main chassis, as you would expect from them, of course. Really nothing else going on. A few switch components here. You can see again the differences in the isolation, how they were planning to do it. I actually don't know what they did in the final version, but again, it's going to be one of these two. This is a bit cheaper to implement because it doesn't have holes and a front end that screws into it, but you know, we have to see which one, how it performs regardless. And the back of the various components, you can see all the different capacitors that you have, and here is the back of the high-speed connectors, and here's the back of the different front-end analog. And you can see the stitching of the wall that I was talking about that follows the traces. You can see the stitching goes throughout the entire board. Yeah, looks really good. And here is the front end channel. Where is channel 1? This is channel 1. This is the other channel. And you can see they're taking some additional signal over here and passing it into this, which is next to the trigger, and this is most likely where the multiplexing happens of the difference in the trigger between these two channels, because this is channel 1, I believe. Yep, this is channel 1. That means the channels 5 to 8 are treated a little bit differently, and that's most likely what is the difference between the triggering system of these two channels over here. So that kind of makes sense too. Now let's look at the magic, which is the acquisition board. And here is the acquisition board, and it's amazing what is actually on this board. So let's analyze it a little bit. First of all, it has a few DC-DC converters. These are the linear micro modules. I would argue that these are probably the world's best, smallest footprint DC-DC converters for high performance devices. It's just that they're quite expensive. So they have a few of them in here because space is really valuable, of course. I've taken the heat sinks off, and you can't see anything because these are fully packaged, of course, but at least you can kind of get an idea of the rough size of the package here. We have 4 differential lines coming in. So this on the other side is the analog connector. We'll take a look at the other side of the board in detail as well. Now, once that data comes in, now this differential that goes directly into the A to D converter. So this is a 4-channel, 16 gigasample per second, 10-bit converter, which is coming from the same family as what creates the 64 gigasample per second A to D converter as one of the sub-acquisition parts of the UXR. So you can see how that's ultimately from the same components. It's a new IC made for the MXR, of course. So these 4 lines coming in, now the data that comes out of the data converters here is enormous amount. I mean, 64 gigasample per second at 10-bit, that's a lot of data. So all of that has to be processed somehow, and then all the magic then happens in this IC. This is a custom IC as well in CMOS that Keysight has made. This has 100 million gates, capable of 5 trillion integer operations per second. So all the computation done on the data coming from here, and how all the advanced functions such as the digital down conversion, the real-time spectrum analyzer, all of that happens in here. So what they do is quite clever. Depending on what you want to do with the instrument, whether it's DDC, digital down conversion, or RTSA, real-time spectrum analyzer, the way they handle, decimate, and store and rotate the sample memory will give you different performances of the instrument. We will see that in details in the measurement. These are some clever, of course, design choices. As this is what I was saying, is that oscilloscopes are no longer digitization and display. They're these massive computational engines that do different things with the data. At the same time, you have to now store this. And Keysight, I would say it's unique in the way it does this because they're using HMC memory, which is ultra high speed, meaning that you have the same memory interface performance. You have no drop in sampling, you have no drop in any performance no matter how many channels you enable, because this 1.6 gigapoints of memory always has the fast interface no matter what, and that gives you 400 million points per channel independent of how you use them, which of course is a huge advantage when you want to use all of the 8 channels at the same time. So let's flip this to the other side. There we go. And on the other side, you can see the amount of work that needs to get done in order to make sure that there's a stable DC going in. There's a lot of capacitors here going in the back of the custom IC from Keysight over here. Here's the A to D converter, and here's the hypercube memory at the back, digital interface connector, another micromodule DC converters, and a bunch of other supporting circuitry. Now, if I also zoom in, you will notice that what they're doing to this board, it's going to be difficult to get this to focus, but there it is. You can see that what they're doing back drilling. And the back drilling essentially means you don't have to have blind vias. That reduces the cost of this board again, because this is such a big board with so many lamination layers that this back drilling ends up being more cost effective. Now, back drilling is needed because the interface between the memory and the FPGA is so fast. These are fast SerDes that have to get the data in and out of the memory, that you cannot have hanging vias on these traces. So by back drilling them, you're essentially performing a type of equalization on the channel, removing stubs that would be hanging. This can create reflections and pretty bad frequency responses. So there's a lot of back drilling, as you can see, going on at the back of this acquisition board. And here we have one IC here. This is most likely where the clock comes in, and you can see the split over here to the memory in over here. And I don't know where the data converter gets it, but I think those are some outputs probably go underneath to reach this data converter at some point, because obviously that's going to need clocking as well. Overall, it's a beautiful piece of engineering just to hold in your hand a complete acquisition system with digital down conversion, with RTSA, and everything that goes in between is really quite impressive. So I think that covers basically everything to say, at least on the surface, about this board. We should now go ahead and play with the unit. And here's the instrument powered on, and it is a little loud. I would say it's a compromise on having 8 channels on a very, very small footprint. I believe most of the noise is from the power supply, so because the fans have to run very fast. But it's something that hopefully you'll get used to as time passes on. So I'm not going to show you the instrument like this most of the time. I'm going to capture the screen on my video capture device because I think the picture would come out much more clear. Let's go ahead and turn all the channels on. You can see we have an LED over here which lights up as whichever channel is selected, and here are all the 8 channels now on top of each other. We can also tile them. I mean, you wouldn't necessarily use it like this, but if you tile them like that, you will get all the individual channels. I mean, it's a beautiful thing. Look at this. You can also combine this. These are basic GUI performances of this instrument, very similar to the S-Series, which I reviewed. This is an evolution of the software with some of the added features. So what I want to do is, instead of going through all the time domain measurements initially, I want to show you the differences between time domain, digital down conversion, and RTSA on this instrument, and how they differ and what kind of compromises are between them and in which scenarios you can use them. I also want to push it to the edge of its performance so we can see what kind of noise we can get and how we can use the RTSA in the presence of, let's say, some blockers. So let's go ahead and capture this and start some experiments. Okay, so here's the setup of our first experiment. We have some mystery RF board here. This is generating some unwanted tones and some weird spurious behavior. I'm going to analyze this using the MXR. Now normally you don't use an oscilloscope for this, you would use a spectrum analyzer, but of course MXR is supposed to be a multifunctional unit. We're going to push it to its limit and see if we can detect our problem. Now to make the job even harder, I have an attenuator here at the output, so we can make the signal arbitrarily small and really push the MXR to the edge of its dynamic range. And even on top of that, I have a power combiner here, and using this power combiner, I'm going to inject a blocker signal or an unwanted signal using the Keysight EXG into the same signal flow, which means that the MXR is not only going to see the signal we're trying to analyze, but it's also going to see the blocker signal. And that blocker signal may not be in the frequency range we're looking for, but of course the data converter will see that signal at the same time. So I want to see what happens when we really push this. And this is a fairly common scenario. There are many situations where you're trying to debug a signal in the presence of many other signals, and of course they are going to interact with each other. So let's see how the MXR behaves here. So let's go ahead and really analyze the signal that's connected to the instrument right now. So we see nothing because we are on a 1 mega ohm input. Let's change that to 50 ohm. There we go. And you still see nothing because the signal is really small. So I want to push the instrument to the edge of its performance, so I have a really tiny signal here. Let's go ahead to 1 millivolt per division, which is the minimum vertical division in hardware this instrument supports. So right off the bat, you can see that this signal is pretty complex. It's obviously made more than one tone because you see a beat frequency around the 2 tones together. So we want to analyze this. Let's take a look and see what kind of tone we have. Let's go and zoom in a bit in the time domain. There we go. So there is some sinusoid. It's quite noisy and you don't know much about what it's doing, and that's because you are looking at a 6.3 gigahertz span. So there's a lot of noise that is going to be on this signal, just inherent from its large bandwidth. Most of it you have absolutely no interest in, but of course you're stuck with it because we're in the time domain. Let's go and measure the frequency of this signal. What do we have? We have something around 2.4, 2.45 gigahertz. Okay, so we can go ahead and take a look at it. So what would you do in this situation? Well, you would take an FFT in order to figure out the frequency content of this signal. We can of course do that here too. Let's go and delete this. We don't need this one. And let's go over here and make a new math function. And we have a huge list of math functions. Of course, let's take an FFT. Here's our first FFT over here. There it is. So what is the disadvantage with a classical FFT? Well, the disadvantage is that you're looking at a huge bandwidth and you're looking at a long capture duration if you want to have good resolution bandwidth, which means most of the data you capture is really not of interest to you because you're looking for a very narrow frequency content in this case. That's what spectrum analyzers do really well. They have a pre-selector and they're looking at a very narrow frequency, but oscilloscopes don't work this way. And this is what MXR is going to change. So let's go and change the center frequency. Let's put that at 2.445 gigahertz. There we go. There's our tone or multiple tones. Let's change the span. We don't really want 8 gigahertz. That's crazy. Let's go at 40 megahertz. And right now the resolution bandwidth is huge, so you just see a flat line. And let's change that. And as we change the resolution bandwidth, our capture duration changes, of course. And let's go all the way down to a resolution bandwidth of 20 kilohertz. And take a look at that. We indeed have 2 tones. You can see that the tone on the right has slightly more phase noise on it. That's to be expected because the tone on the left is coming from the Keysight EXG, which is going to have a much better phase noise than something coming from a PCB. Okay, that looks okay. There's nothing unusual really going on here, and it doesn't appear that these tones are doing anything interesting. But in reality, these tones are a lot more complex than the FFT allows you to believe. And the reason is because even though the MXR has an extremely fast FFT, it's just not going to have the opted rate needed to capture some of these tiny differences between these signals. So what are the different modes of operation? Well, I've produced this table here. You can pause the video and read it, but I'll tell you the main points. In the classic time domain and FFT is what oscilloscopes do in general. That's what you're familiar with, and even though the MXR is really fast, you're always going to have the limitations on taking an FFT on the entire capture. Now what the new MXR has is that it has the digital down conversion mode, meaning that it allows you to look at up to 2 GHz of span on all the channels independently using the ASIC built into the system in order to give you much higher capture rate. And if you combine that with the VSA software, which we will do later on in our experiments, you will have this extremely powerful 2 GHz bandwidth on 8 channels where you can do all kind of complex wireless system analysis on it. That makes this a really good tool for 6G and 5G experiments, because you have so many parallel channels. If you want to do MIMO, if you want to do some kind of multiple transmitters and receivers operating at the same time, you want to see the interactions. That's exactly the instrument intended for. Over here in the DDC mode, you still have a lot faster capture rate than you had using a traditional FFT, but really in the real-time spectrum analyzer is where this thing goes crazy. Here you have 320 megahertz span maximum, and you have to share that between the channels, but it captures so fast that you can capture a 15 microsecond interval signal with 100% probability of intercept at full amplitude. These numbers are unheard of for, of course, oscilloscopes. That's what spectrum analyzers with real-time analysis do. And that's why the MXR is a multi-instrument in one in general, because of its abilities. Now, each of these modes have some compromises that you have to know. And what the instrument does is that it tells you both the compromises and the strengths, so you can hone in on what you're looking for and switch between different modes of operation in order to get the work that you want done. So let's go ahead and give that a try. Let's give DDC a try over here. So I'm going to go and remove the FFT. We're not going to look at it anymore. And instead, I'm going to go over here. I'm going to change the signal type. Instead of unspecified, we can make it to be a spectrum analysis signal. And as soon as I select that, the instrument changes completely. It eliminates all the time domain signal, and it puts us in a purely spectrum domain. I'm going to go ahead and change this to a 10 dB per division as well. And the center frequency is 400. That's not what we were looking for. Let's go back to 2.445 gigahertz. And here's our signal. And right now the span is 320 megahertz. You can go all the way up to 2 gigahertz, as I mentioned, but let's go back to 40 megahertz. Now 40 meg is the minimum. Unfortunately, you cannot go smaller. It'd be nice to look in a little bit closer, but there are some limitations in the hardware, I believe, that causes that. And look at that. This is already very different than our fast Fourier transform. This signal has a lot more frequency, agility, and content that we thought it did. And there's a lot of other stuff that happens that were completely invisible to us in the other mode. Now, one thing to consider is that in the DDC, in the current firmware revision, you only have triggering in the time domain. So you cannot trigger in the frequency, phase, or amplitude. You would have to trigger in the classical time domain signals. I hope they change this, because if you add that to this instrument, it becomes much more powerful, as you can catch these things in a trigger domain, as well as just looking at it in the time domain, the frequency domain. So that's great. It's still not quite fast enough for what I want. I really want to be able to catch these infrequent events. For instance, the activity happening over here is even more infrequent than the activity happening over here. So I really want to catch them at the same time. And by the way, this screen sometimes pausing, that has nothing to do with the scope. The scope is much faster. This has to do with my video capture device that's sometimes missing some of these signals. Let's go ahead and change the mode again. Let's go to RTSA. And here is where you really see the difference. And you can see how much faster this instrument is. It's catching every single thing that comes in, and we can see all the different activities. For instance, the phase noise is very clear, the difference between these two, and there's no compromise on the noise floor. We're still looking at a minus 108 dBm signal, which is crazy. Again, for an oscilloscope, shows you how low noise this entire system actually is. This is our main tone. You can see it jumps back and forth between these two frequencies. This other signal occasionally seems to be jumping here. This is really, really infrequent. And these other signals that come and go, these are actually Wi-Fi and Bluetooth that get coupled into the PCB that I just showed you earlier. The instrument is so sensitive that it's picking up all of those, and the board is acting like an antenna. Normally these are all invisible because you don't have an instrument that's this low noise normally. So what can I do to capture this infrequent event a little bit more? Well, there is a built-in frequency mask triggering right now. You can go ahead and enable that and draw a new mask. And what I can do is I can add a zone, and I request that to only show me the signal when there's an intersect between the zone and the captured spectrum. So let's go ahead and put that over here. I don't really want this point here. Get rid of that. We're going to put it over here and put this over here. So right now what this tells the instrument is that if there is a signal present within this yellow square, then show that to me. So let's go ahead and click OK and wait and see what happens. There you go. You can see every once in a while we get some measurement. Now there is a bit of a weirdness in the firmware right now where once something is captured, you cannot hold on to it on the screen, which means that it is acting like a filter rather than acting like a trigger. And I think they're going to change that so that if you do a single capture trigger and you capture something, it will just hold it for you at that point. So what does this mean? It means that this signal, if you look, it happens once every 1.3 seconds or so. So it's really, really infrequent. The fact that we can catch it is really valuable. And you can see when we do catch it, that this other signal is also present. So what can we do here? We can change the display a little bit, get a bit of help. Let's maybe make this a 5-second intensity there. There you go, look at that. So that signal is happening every once in a while. Now right now, this triggering doesn't allow you to capture the raw data. And again, I hope they change that. There's so much potential in the MXR if they have a few of these additions, the triggering in the frequency domain, being able to offload this data and keep it on the screen. These are hopefully something that can be implemented. But I hope this gives you an idea about how powerful this system can become, because you can now jump back and forth and capture these really strange events that normally are invisible to oscilloscopes. And here I have moved the frequency mask trigger to this point in the spectrum, and that means that I am catching every time this tone jumps to this position. And you can see that we don't see any activity over here, and that tells us something important, that this glitch on this tone is completely uncorrelated with a glitch on this tone, and they don't really happen at the same time very often. I can change the mask. Instead of saying intersect, I can say it must not intersect, and now I will catch only when the signal is not there, and now I will catch the other position happening. So there's a lot of flexibility, of course. By playing with this, you can put multiple zones and capture different things. Really quite powerful. Now I also want to try out and see what is the largest dynamic range I can actually capture. What's the smallest signal in the presence of a blocker that still allows me to capture something meaningful? I'm going to set that up. Let's go ahead and actually remove all these zones and just capture the spectrum as it is. I'm going to go ahead and reduce the amplitude of our signal until it's really, really small. Let's say we bring it somewhere around minus 100 dBm. So that tone is really, really tiny. I'm going to increase the blocker and see at what point we can no longer capture it. There you go. The blocker is getting bigger and bigger. And at some point in the top left corner of the screen, you're going to see a warning, and that's the instrument tells us, there you go, we have an ADC clipping situation. And as soon as I increase it beyond that, there you go. Now these are all the harmonics generated because the ADC is saturated. So let's go just underneath the ADC clipping range. Let's say somewhere around here, there you go. And we're looking at a signal that's about minus 37, minus 35 dBm. So I'm putting in a minus 35 dBm signal, and I'm capturing a minus 100 dBm signal, which is only a few megahertz away from it. This is really, really good, and tells you the extended dynamic range and the linearity of the entire system, and that's what I was expecting from an instrument like this anyway. And this is powerful because it means there are multiple things you can capture at the same time without them interfering with each other. So for our second experiment, we're going to try out another new feature of the Keysight MXR. Keysight claims that the MXR has an incredibly accurate internal time base. Of course, it's also very low jitter. In fact, it's supposed to be so good that they have included a 10-bit counter built into the unit itself. That's a pretty big claim, so we're going to test that out. Here I have the Tektronix TSG4106A. This unit has a built-in oven-controlled crystal oscillator. It's a very large unit, and in fact this produces very high accuracy frequency. I've split it into two. It goes into channel 1 on one of the outputs, and on the other output it goes into a rubidium counter, so we can measure this against an atomic reference to really know the exact frequency coming out. At the same time, I have the Signal Hound PNCS1. This is a 1 GHz frequency reference for ultra-low jitter measurements, and I want to measure this guy's frequency as well. Normally you would do this with a frequency counter or even a rubidium frequency counter. We're going to try and see if this unit can do the job. So let's go ahead and try to do this measurement. So here's my channel 1 signal. This is a 1 GHz tone that I'm feeding into the instrument, and I can go ahead and measure a time domain measurement taken on it. Pretty straightforward. You can see it's about 1 GHz. Now of course this measurement here is done on the captured data. It's mathematically computed based on the data that's in the memory. So if I go ahead and turn off this data, or this channel, this data will go away because it's connected to the channel, of course. Let's turn it back on over here. So let's go ahead and also enable channel 2. Here's channel 2. And as soon as I enable channel 2, you can see that because I'm triggering on channel 1, even though the frequency of the second channel, which is coming from the Signal Hound reference, is close to channel 1, it doesn't have to be that far for us to not see anything, because the phase of the second channel is constantly rotating with respect to the first one, and we're doing an edge trigger on the first channel, and therefore the other one is not coherent and you won't be able to see it. So let me go ahead and delete this measurement. I want to find out exactly how far these two frequencies are from each other. We can also measure the amplitude of this using the built-in DVM. Here it is. So let's say channel 1 ACRMS. Let's enable that. And why is this special? Well, it's because it's not done using the captured data in the same way as we do the other measurement I was showing. So if I go over here and if I turn channel 1 off, you can see that this measurement does not disappear. So you don't even have to have that channel enabled in order to get this DVM measurement. Let's turn this back on again. So what is the frequency of channel 1? Well, we expect it to be about 1 GHz, but how good is this instrument in measuring it? Let's go over here. Let's enable the counter. And here's the counter. You can have two counters on at the same time. You can choose between channel 1 to 4. You cannot use 5 to 8, and that has to do with the triggering, I believe, because the first 4 channels go into this special ASIC for triggering. And we can go all the way up to 10 digits, which is quite amazing. Let's see what happens. Let's turn channel 1 on. That's the second one on. You can also do a ratio between them. That's already selected. Now, because there are so many digits here, we have to wait a little bit until the counter builds enough accuracy and confidence to be able to give us an exact measurement. It's going to show up any second now. And let's see what we get between the two channels. Here we go. Take a look. So this is, well, this is a lot of digits. This last digit over here, this is in 0.1 hertz. So you can see if I were to compare these two with each other, they're really not that far off from each other. This is 51 hertz at the end. This is 93 hertz at the end. So we're talking about only 40 hertz of difference between them. And you can see that over here in the ratio measurement as well, because it's close to 1. That's why it shows up like that. So, well, how good is this if I were to compare this with the rubidium standard? Well, I have a live camera on the rubidium 2. And turn that on. And here it is. And check this out. I mean, this is a really, really impressive measurement. Look at that. That ends in 933. This ends in 934. That one is an atomic reference. We're comparing something without an atomic reference to a rubidium standard, and they're essentially 1-to-1. This is really impressive. Now, why is this useful in an oscilloscope? Because traditionally you couldn't do this in an oscilloscope. Let's say you have a SerDes or you have a wireless transmitter, and you want to find out the difference between two crystals, between a transmit and receive, or you want to compare your internal clock to, let's say, the GPS clock. Well, you can do that with the oscilloscope by directly feeding it into the unit. And you don't have to be capturing this data. These are done independent of the channel measurements. I think this is really an amazing feature they included for debugging of SerDes and wireless systems, being able to be done instead of using a frequency counter. So here's the setup of our next experiment. Here I have 10-inch of backplane, and I have an amplifier in the front which is driving the backplane. This can be like a serial communication link on some backplane PCB, and I want to find out a couple of issues that it has. So the data coming into it is coming from a serial birth. The serial birth is sitting all the way over there, so I can generate pretty much any data rate that I want to, and I can impose some impairments on this link via this amplifier in the front. And the output of that is taken directly into, of course, our oscilloscope. So let's go ahead and try and see how the oscilloscope's built-in fault-finding functions as well as equalization and eye captures look on the new MXR. So here's a data stream being captured with channel 1 of the oscilloscope. Let me go ahead and change the trigger so we can see a somewhat better eye. There we go. Here it is. So you can see that the eye diagram here in the time domain being captured just using regular sampling is really open. And that's not surprising because this is a fairly high bandwidth backplane as well as a high bandwidth amplifier, and it supports 1.25 gigabit per second fairly easily. That's the data rate of this signal coming through. Now, there is a problem with this signal. It has a very infrequent, unusual glitch on it. Now, to make matters worse, this glitch is completely uncorrelated with the data stream itself. It means that it can happen at any time, at any point in the data stream, and can be completely different every time. And that makes it very hard to find using traditional methods. But it is very infrequent, which means that you would have to search for it as well for quite some time to get it. It seems like a perfect candidate for the new fault finder function that's built into the oscilloscope. So let's go over here. You can see under Analyze, I have Fault Hunter. We can run that. You go, I can just set it up myself, but there's an auto setup here. I'm curious to see how well the auto setup would work. Here's the auto setup, and the way it works is it will start capturing a lot of data and begin to build a statistical distribution of how the signal behaves on average. So if there is an outlying event, it will be a perfect thing for it to catch because it will be totally different from how the signal is normally behaving. Now, depending on the signal, it can take sometimes more, sometimes less, about a minute maybe to run this. But of course, it's capturing a ton of data and processing in the background. So soon you'll see a list of tests that it's going to bring up, and we can see what kind of test is running. It should be there any second now. You can see it also changes all the other settings automatically. There you go. You can see it's already failing positive glitch, negative glitch, and the rise and fall time. It's also even failing the runt. So the rising and falling edge can fail in a test like this if you have some bandwidth limitation, because you will have data dependent jitter, and a data dependent jitter, especially for a long sequence of data, can appear as a failure. But we're not interested in that so much. We're mostly interested in why is the positive and negative glitches failing. So we can go ahead and say view. It's going to create for us a point in here. There you go. You can already see the problem. Look at the amplitude of this signal. Look how small it is during this capture. But this is a representation of the data normally. So clearly there is a problem. Let's try a different one. Let's try this one. There you go. You can see another problem. The zero crossing is completely wrong here, so it has caught that as a problem. Remember, these are really infrequent. You couldn't really see them when the data was being displayed because they happen, once every few seconds, and they are there for a very, very short amount of time. So what we can do, which is really useful, is to copy this failure into the trigger. Now, as soon as you put that into the trigger function, we can go ahead and begin running this. And then the oscilloscope will now capture only when that fault happens, which is a huge, huge help. So let me go ahead and zoom out over here so you can see for yourself. I'm going to continue to zoom out. Let's go to here and check it out. Look at that. There is a major problem in this eye going through it. At some point the data is there, then something happens, it disappears and it comes back and it goes back to normal. And this happens once every couple of seconds. But of course, all of this is being done automatically. The type of trigger you need to do, how it's set up, the values it needs to have, so you can immediately jump and find a fault. I find this to be really quite useful. And of course, you can set all of this manually. But this fault hunter can also get more and more powerful over time. For instance, you can have a database that you can go look up for typical failures. I think this is a pretty neat idea. Let's see how it evolves over time. So now that we found this fault, I'm going to go ahead and remove the fault from the signal, but I'm also going to increase the data rate to 3.125 gigabit per second, basically pushing the backplane far beyond it is designed for, so we can see how the eye looks like then. So let's go ahead and increase the data rate from 1.25 gigabit per second to now 3.5 gigabit per second. So this is a big jump, and naturally we're going to see quite a bit more degradation on the actual eye diagram. And we can see that the NRZ eye has turned into a bit of a do binary eye. And this is normal for an NRZ eye to do this if it is encountering a low-pass filter channel that has a particular phase response. So it's a reasonably well-behaved channel. That's why we still see a nice do binary with 3 distinct openings. But I want to know what kind of jitter I'm dealing with. I also want to know what kind of equalization I need to bring this back into an open eye, eliminating most of this do binary behavior. So first thing is to capture an eye. I can go under analysis and I can go under real-time eye. So what is special about real-time eye anyway? Normally when you want to build an eye diagram, you do multiple acquisitions and then you overlap the waveforms to build your eye. What the MXR does is that instead it takes a deep acquisition without having to re-trigger, and therefore it's significantly faster, but it still allows you to unroll and open the eye back up in order to figure out an individual bit that has gone wrong. So this unrolling of the eye combined with the speed allows you to build an eye diagram very fast and not lose the ability to debug and find a fault in a mask, for example. So this is a pretty powerful thing. Let's take a look at it. I'm going to go ahead and enable it here. I'm going to do an auto threshold, and I'm going to do an auto clock recovery. There it is. I think it has figured out the clock recovery itself. Let's go under the second order PLL here. You can see it has found roughly the correct data rate, and it has all the settings of the PLL you would want to set up. You can just continue going down the rabbit hole and set all of these things manually if you want to. You can even enter my own data rate. This is a 3.5 gig. Of course, it makes no difference because it's in a CDR anyway. Okay, I think it looks good. Let's go over here. I'm going to bring a few more eyes so we can take a look at the eye over here. And let's close that, and let's bring this down here. First of all, take a look at how ridiculously fast this is and how much data is being recorded and built. This is a huge amount of computation. Now, if you also look at this eye, you can see that the opening, vertical opening, is not very good. There's a lot of ISI on it. The horizontal opening is good. The jitter is not so bad. And of course, the do binary top and the bottom are even bigger than the middle one. So that's a consequence of the channel, of course. So let's say I want to now figure out what kind of jitter I'm dealing with. We can use again another built-in tool here. And some of these are, of course, licenses you have to purchase. This is a fully loaded instrument. That's why everything is enabled. Let's go under jitter here. So I can go and enable the jitter. And I can do a quick set. Let's see if we can figure it out itself. If not, we're going to have to help it with the data rate. I think it's going to need a bit of a help. Yep, it's confused. The eye is not very good. So you're going to have to give it a little bit of help to figure out which eye it's looking at. There it is. Let's see if it can do it now. There it is. There you go. It figured everything out for us. Let's make this a little bit larger. So here is our composite total jitter histogram here. You can see the total jitter over here. A lot of data dependent jitter as to be expected, but it's not really as bad as the total value of the random jitter. And you can see that because the horizontal eye opening is not very bad. At the same time, we have a bathtub curve. We can go ahead and enable some other plot. Let's take a look at, for an example, data dependent jitter versus bit to see it as a function of our sequence. Here we go. So at the bottom we have 2048 bits. That's indeed the length of the pattern. It's a fairly short pattern, but you can then find out which of the bits caused the worst case of the ISI. These analyses are fairly common for eye diagrams, and these toolkits are built directly into the scope, and they do take advantage of some of the ASIC functions of the scope as well in order to run much faster. Okay, so that's our jitter. We can go down and do a lot more tests under, but I just want to show you that it's really quite easy to capture an eye and very quickly be in the jitter domain and figure out what's going on. So let's put the jitter aside for a moment and turn it off. Go back to the regular eye diagram over here. Here we go. Now I want to equalize this eye and see what kind of coefficients I need to bring this back into a fairly good open eye. Under analysis, we can choose now equalization, and the instrument supports a fairly comprehensive set of equalization functions. We have continuous time linear equalizer, feed-forward equalizer, and decision feedback equalizer. We can set all of them up separately. I like the FFE in particular because it allows us to do an auto set on the taps, and then we can adjust the taps to see how it affects the eye. Let's see, how many taps do we want? Well, let's push the instrument really hard. Let's say we can do 10 taps. That's a lot. And we do even 5 precursor taps. So that's a lot of coefficients for this instrument to try and open the eye. I'm going to go ahead and enable the FFE. I'm going to go under auto set and then run the auto set. There we go. Even though it says this optimization is working, it actually does do it in the background. I'm not sure why the label doesn't change, but let me go and turn this on. So as soon as I turn it on, yes, there are two things you can do. You can either equalize this in place, meaning that it will apply the equalization on the same eye diagram, so you're seeing it both after equalization, or you can say display it as a function. When you display it as a function, you have the option of turning it into a totally separate eye diagram, and that will be displayed at the bottom. We can go ahead and close that and check it out. Here's our equalized eye. In fact, let me go over here. Let me make them the same in terms of how many UIs we're looking at, so it becomes a lot easier to compare. There we go. Let's close that. Let me do another auto set here. Let's see if it does the auto set. There you go, running equalizer. Now it has a pop-up window. There you go, so you can see it did do it. Here's our eye, and I can go over here and I can look at these tabs individually. This is a there's a lot of taps being applied. So the instrument does a lot of background computation to bring this, to display it. Let's take a look at it and see what we have. And check it out. Most of the do binary function is almost completely gone because of the equalization. Of course, the eye is much more open compared to what we started with. We can see the original waveform as well as the equalized waveform on top of each other. And is running all of these at the same time, and it has already built 2.2 million UIs on the equalized eye too. If you're in this domain and work with these kind of functions all the time, you can appreciate how much is being done in the background. Now, I'm doing this only on one channel. You can do it, of course, on 8 channels, and there will be a penalty for having more stuff to be computed and displayed, but there is a ton of stuff you can do in the background on this instrument. Really quite impressive. So in the interest of time, let's pause here for the first part review of the Keysight MXR. This will also give you an opportunity to ask questions in the comment section for the second part review of this, where I'm going to dive into the system level measurements. We're going to bring VSA into the equation. We're going to do a lot of wireless testing and show really more of the capabilities, especially the software capabilities that are built into the unit. There's just so much you can do with an instrument like this. And of course, the fact that this is based on the UXR architecture and being an 8-channel oscilloscope with all the ASIC functions built into it makes it a really good, attractive upgrade to the S-Series. And at some point, we would like to compare this to some of the competition as well. Hopefully, we will do that in the second part. But yeah, I've been really quite happy about it. There are very few things that can find fault with it. I still think that it has a lot of potential if they additionally include some of the new firmware functions that I discussed here in the review. I hope you liked this. As always, if you did, please let Keysight know. Of course, I don't get any benefit from the sales of this instrument, but it does allow me to have a good relationship with the vendor so I can do these kind of nice equipment reviews for you guys in the future. In the meanwhile, I'll see you in the comment section.